All right, we're recording. Thank you.
Is that all I need to do?
Yep, that's it. As you were.
Thank you. Thank you. It's wonderful to have a guide. Okay. So are there any questions about what I just said about non-dimensionalizing this equation? And then I'll talk about non-dimensionalizing this equation in just a moment. But are you okay on that? When you non-dimensionalize this equation, non-dimensionalize the lift, of course, you're going to get the lift coefficient. That's the definition of the lift coefficient. Do I hear any questions? Hearing none. Oh, yes, go ahead.
Do you want the CL or the CL alpha?
Well, in this case, it's going to be just CL because we're going to, it's really both in a way, because if I set dHdt over U infinity equal to 1, that effectively is an equivalent alpha, because alpha, which is an equivalent angle, is really the vertical velocity of the airfoil, which in this case is dHdt, divided by the horizontal velocity of the flow. So the answer to your question in practical computational terms is both, because we've effectively set the equivalent alpha equal to 1 by setting dHdt over U infinity equal to 1. Does that help?
Yeah, it does. Thank you very much.
You're welcome. So when you do all that wonderful non-dimensionalization, including non-dimensionalized time in the usual way, that you're going to non-dimensionalize time, both tau and t, by multiplying t or tau by U infinity and dividing by 2b, right? That's how we normalize time. It's sort of the inverse of the way we normalize frequency. Then this will all be in nice non-dimensional form, and you can plot CL versus non-dimensional time. And the only parameter that will appear then, once you've non-dimensionalized, the only remaining parameter will be, in fact, the Mach number, which I gave you. I told you the Mach number was either 2 or 1.2. I think those are the two values we chose. So are we all right with that?
Yeah, Professor, can you show us like what the solution should look like?
Yes, I will in just a moment.
Okay, thank you.
You're welcome. You're welcome. Aha, you're anticipating. See, I'm such a nice guy. I'm going to show you what the solution should look like. Before I do that, let me point out what you're going to do with K, because you're going to need K in order to evaluate L, or the non-dimensional L. This is the formal expression for K that comes out of the analysis, which I hope you read and understood. But then you can simplify this formula to the following formula by taking advantage of the way that alpha appears in this equation, because the imaginary part of this equation will turn out to be identically 0, and you should be able to show that analytically by using the fact that the imaginary part will be odd in alpha. That is, the solution for the imaginary part from minus infinity to 0 is equal and opposite in sign to the solution from 0 to plus infinity. So the imaginary part goes away. And what remains is just the real part of this expression, which is this formula. But then when you integrate this, remember you're going to non-dimensionalize time, but you also need to non-dimensionalize alpha. And alpha has dimensions, it's a Fourier transform variable in space, so it has dimensions of 1 over length. So if I multiply alpha by 2b, I will non-dimensionalize alpha. And note that if I multiply this alpha by 2b, and then the d alpha by 2b, then that's fair enough, right? I've multiplied and divided by the same thing, so I haven't changed the value of the formula. In this cosine factor, automatically you have this combination of alpha times 2b. And then in this Bessel function and this cosine function, these are the dimensional t and tau, but when you non-dimensionalize this by multiplying the t and the tau by U infinity over 2b, then if I'm going to multiply by u infinity over 2b, I need to divide by u infinity over 2b, and that will non-dimensionalize the alpha and also give me a factor that only involves the Mach number. In fact, it looks to me like the Mach number is going to cancel in this factor, and over here you'll have a factor that goes like 1 over the Mach number. So I'm saying you need to non-dimensionalize t and tau in this equation, and also non-dimensionalize alpha. But if you do that, then this whole equation will be in terms of a non-dimensionalized alpha, which you're going to integrate from 0 to infinity, and a parameter Mach number, which will appear in the argument of this Bessel function. So does that help you? I hope.
Yes, this is helpful. Thank you, Professor.
Okay, now you asked, could we see what the answer actually looks like? Well, I'm happy you asked that question. So let's go down further in the book. I'm going to skip over some additional analysis and show you some results, which I think you'll appreciate. At least I hope you will. Let's see now. Here we go. Okay, well, let me first of all show you the result that you're probably most interested in. And let me go back down here. Here we are. Someone asked me a moment ago, are we computing CL or CL alpha? And I said, yes, we're computing both because we've taken the equivalent alpha, the equivalent angle of attack, which is this dH dt divided by u infinity and set it equal to 1. So if we do that, then it's whether CL or CL over alpha, since alpha is 1, it's the same thing. So this plots CL alpha, or CL divided by alpha, where the alpha is 1, versus S. In this case, the authors who originally obtained this result were some, at the time, famous aerodynamicists at what was then the NACA, before it was NASA. And they, in their wisdom, chose to non-dimensionalize time not by C, the chord, but by C over 2, which is equal to B, right? So you need to take that into account when you compare your results to theirs. But with that little difference in non-dimensionalization, here's what the lift coefficient looks like as a function of time, non-dimensional time, S, for different Mach numbers. Here's a Mach number 1, here's 0.8, here's 0.5, here's 0, here's 1.2, which is your magic Mach number, one of your two magic Mach numbers, and here's 2, which is your other magic Mach number, okay? So when you get your results for CL alpha, you should have a result that looks like this curve for Mach number 2, and like this curve for Mach number 1.2. So what does this say? At time t equals 0, you're going to get a value of 2, okay? And that's the value given by piston theory. Remember we briefly discussed piston theory? And then at very large times, it goes to the steady state value, which is basically what is it? It's slightly bigger, and it's the difference between the factor of Mach number and Mach number squared minus 1 square rooted. But the point is that at Mach 2, the result at short time given by piston theory and the result at large time, which is basically the steady flow result, they're very close, right? There's not much difference, which tells you that at high Mach numbers, piston theory gives you a pretty good answer, although strictly speaking, it's only the right answer at short times. It really is a pretty good approximation for a large time. And if I looked at a Mach number like 4, all of these results, this factor of 2 would go down to a factor of 1. And then the difference between this curve and this horizontal line would be even smaller. And in the limit of a high Mach number, you get basically just a horizontal line. The result wouldn't depend on time at all at high Mach numbers, according to this potential flow model. On the other hand, when I'm down here at a Mach number 1.2, right? Again, piston theory, piston theory gives you the right answer at short time. This is still the result given by piston. Piston theory basically says CL alpha is 4 divided by the Mach number. So 4 divided by Mach number 2 gives you 2, and 4 divided by 1.2 gives you this factor that's a bit over 3. And so this is still piston theory at short times, but then as time goes on, this rises, and at a large time, the result is quite different from what piston theory would give you. So piston theory gives you a very bad answer at large time, at this Mach number. And then let's look at some other Mach numbers. I'm sorry this curve is so busy, but it pays some close attention. Here's the curve for Mach number 1. Again, piston theory actually gives you the right answer at short time. It's 4 divided by the Mach number, or in this case, 4 divided by 1, so it's 4. And if you were to do this calculation using the CFD code, or if you were to actually be able to do an experiment, you would probably get an answer that's pretty close to what piston theory gives you for short times. But then what happens at large time is the lift curve slope, or the lift coefficient just keeps going up and up and up. And in fact, it goes off to infinity. So this two-dimensional supersonic theory is breaking down at large time as you go to the steady flow limit. Remember, physically, what we're doing is we're thinking of this airfoil will be given either a step change in angle of attack to a constant value, or a step change in downwash dHdt divided by U infinity. And at large time, at Mach number 1, you never reach a steady flow condition. It blows up, which is an indication that the theory is breaking down. And then if you go to other Mach numbers, subsonic Mach numbers, we haven't talked about subsonic flow yet, but we will eventually. Here's the subsonic Mach number of 0.8. This actually goes to a finite result. You don't see it because we haven't drawn the curve out far enough. And then at 0.5, it's the same thing. And at 0.5, remember what happens at short time is still given by piston theory. Piston theory says the result should be 4 divided by the Mach number. So 4 divided by 0.5 is 8. So this is the piston theory result for a Mach number of 0.8. Piston theory is still giving you the right answer, even at subsonic conditions, but at very short times. But then as time goes on, that piston theory value quickly is no longer a good approximation. And so we start out at a large value of the lift coefficient, or the lift curve slope. We go to a minimum value, and then it comes back up and reaches a steady state value at large time. And then here's the curve for the Mach number of 0, right? Now, so here it's going to a steady state value, but if I trace it back to short times, it goes back down to what appears to be this value. But strictly speaking, what happens at time t equals 0, remember piston theory is supposed to give the right answer at short times. It's 4 with the Mach number, but 4 over 0 is a very big number. There's actually a delta function. There's an infinity. The incompressible flow theory itself actually breaks down at short times, which corresponds also to very high frequencies, and it has its own difficulties. That usually is not mentioned in the literature, particularly by those people who like to use incompressible flow theory. but strictly speaking, at short times, the incompressible flow theory has a problem.
Hey,
So
Professor,
I probably, excuse me?
I have a question.
Sure.
So what is like the connection with like the physical phenomena whenever you're talking about a zero Mach number? Like, I mean, you won't have, in my mind, you won't have lift anyway. So why would you produce this line?
Well, yeah, why would I want to do that?
Yeah, exactly.
Because historically, if you go back to the beginning of unsteady aerodynamic theory, people thought that solving the incompressible flow model would be easier than the compressible flow model. In some respects, that is true, but in other respects, it's not. It's true in the following sense. If you go back to the wave equation that we're trying to use as our model, right?
Yeah.
If I set the Mach number, if I non-dimensionalize that equation and set the Mach number 0, that wave equation reduces to the Laplace equation. And there are
Okay.
those people who believe that solving Laplace's equation is easier than solving the wave equation. You could debate that point, but at least at the time this was being done, this is 1930s, people thought that. And so and also airplanes at that time were not flying as fast as they are now, right? So there were
Right.
10 reasons why people would want to look at low speed flows. And when the Mach number gets small, let's say the Mach number, for example, the Mach number in our wind tunnel during a typical test is somewhere around 0.1, right? Maybe
Yeah.
0.2 on a really good day. And so there's a temptation to say, well, it's so small, why not just set the 0 and simplify the mathematics? Well, you can do
Okay.
that. You can do that. You get this curve, but there's this little blip at time t equals 0.
Yep.
And the reason people were willing to accept that blip is because normally they were thinking of some finite frequency. And as long as the frequency is finite, you don't really have to worry about that singularity.
Okay.
Did I tell you more than you wanted to know?
That tells me just enough.
Okay, that's good.
Thank you.
Other questions about this plot? Okay, so
On
now
the
you
other
know
side of the spectrum, sorry.
I'm
On
sorry.
the other side of the spectrum, can you talk about when it
Hello,
did that
Ricky, did you have a
question come
question?
through?
No, Ricky, your connection seemed to fail a little bit there.
Yeah, my internet's not doing so hot. Can you hear me now?
We can.
I can. Mm-hmm.
Can you talk about what would happen on the other end of the spectrum at Machs 3, 4, 5 as you approach hyper?
Yeah. Okay. Well, here's Mach 2, right? Okay. Again, let me tell you what would happen at Mach 4 because it's a factor of 2 and it's easy for me to remember how it goes. At Mach 4, remember, piston theory says CL alpha should be 4 over the Mach number. And you'll see that, by the way, immediately when you non-dimensionalize your equation. So 4 over the Mach number, if the Mach number is now 4, this goes from a value of 2 down to a value of 1, right? It's 4 over 4. And then it goes up a little bit from there. It actually waits a while and then it goes up. But the difference between this curve and this curve is right between the difference between about 2.3 in at large time versus 2 at short times. Here would be 1 versus maybe 1.05 or something like that. It'd be it would almost, as the Mach number gets very high, this result just becomes a horizontal line. That is, the lift does not change as a function of time at very high Mach number, according to this model. Does that help?
Yes, thank you.
Okay, yeah. So people love piston theory because it's simple and it actually gives you the physically right answer if the Mach number is reasonably high. And you know, for some applications, even at Mach 2, that would not be a bad approximation. But clearly, as you get down to the lower Mach numbers, piston theory it tells you something interesting at very short times, but after that, unfortunately, it requires a much more elaborate model than piston theory. Okay, so let's go back. If there are no more questions about this plot, let's go back and talk about some other things. Any more questions about this plot? Hearing none. Let me go back. Oh, I will show you some more results before I do that. Yeah. Okay. This figure 4.10 shows you some more details of the solution for a Mach number 1.2. And what this is showing you is the pressure differential across the airfoil divided by the dynamic pressure, that's Q infinity, that's 1/2 rho infinity U infinity squared, divided by, in this case, alpha, the effective angle of attack, which in our homework problem is just H dot over U infinity. And it shows how the pressure varies along the chord, normalized by the chord. So this goes from 0 to 1. This is the leading edge of the airfoil. This is the trailing edge of the airfoil. And it shows you what the results look like for different values of non-dimensional time S. At S equals 0, it's this horizontal line. That is, piston theory says if I have a constant angle of attack or a constant downwash, then the pressure does not vary along the chord. It's a constant in space along the chord. That's interesting. At large time, the complete theory says that's still true. Namely that the pressure doesn't vary along the chord at very large time. This is the result for time equals to infinity, if you will. But the value of the pressure differential from short time to large time changes quite a bit at this Mach number. At higher Mach numbers, say 2 or even especially say 4, then these two horizontal lines would be much closer together. And again, the theory would say there's no variation in the pressure along the chord. However, at intermediate times, this is a time of 0.8, 3.2, 6.4, the pressure differential can change. It's for example, at 0.8, it's a constant up to this point, and then it drops down here, and then it varies like this along the chord. So the pressure distribution along the chord as time is evolving can vary quite a bit, okay? Particularly at this Mach number. Although, interestingly enough, at very large and very short times, the pressure distribution along the chord is a constant. To the best of my knowledge, no one has ever measured this. One reason that aerodynamic theory has played such a prominent role in aeroelasticity is because, as difficult as the theory is, the measurements are generally even more challenging. So there are not as many unsteady aerodynamic measurements as one might like to have. Let me go back up now and show you a comparable set of results. But now it's for a subsonic Mach number. We haven't talked about subsonic flow yet, I realize, but this is a preview of coming attractions. The pressure distributions in subsonic flow are very different from the pressure distributions in supersonic flow, okay? And again, all these curves, I'm sorry there's so many, but it pays you're looking at them and thinking about them. Here's a curve for time 0, and at time 0, again, it's piston theory, right? And piston theory says the pressure distribution should be constant along the chord. On the other hand, if you get to a very large time, here's a time, the largest time we have is 8. The pressure distribution has a relatively high value near the leading edge, and then it drops down, and then it drops down, and then it drops down, and eventually goes to 0. at the trailing edge. In fact, all of these results at all times, the pressure differential across the airfoil goes to 0 at the trailing edge. And at very near the leading edge, there's a singularity. It's a weak singularity. What do I mean by weak? It means it goes to 0. Excuse me, the pressure goes to infinity, but it goes to infinity like 1 over the square root of x. And if you remember your course in mathematics, that's an integrable singularity. What does that mean? That means if I take this pressure distribution, even though it goes to infinity to the leading edge, and integrate it with respect to x, I still get a finite answer. So I get a finite answer for the lift, I get a finite answer for the moment, I get a finite answer for any integral of the pressure times any weighted function. And so this is still a useful theory, even though I have that singularity. Now, how do I make that singularity go away? Well, you have to put in viscosity, but that takes us to a much more elaborate model. The other thing you should know about subsonic flow is that it's an empirical theory. Aerodynamicists don't like to hear me say that, but it's true. I said all these pressures go to 0 at the trailing edge. Does that come out of the theory? No. The theory says, particularly if you solve the Laplace's equation, which is effectively what we're doing here, or something akin to it, it says that the solution is not unique. Okay, if you try to solve Laplace's equation for the flow around an airfoil, the solution is not unique. There's a whole family of solutions. So given that, how do I decide out of this family of solutions which one is right? Well, you appeal to experiment. And the experiment shows that indeed the pressure in subsonic flow tends to 0 at the trailing edge. And so we impose that condition. That makes the solution unique and also gives us an answer that agrees with the experiment, the limited experiments that have been done. From a mathematical point of view, you could require that the pressure difference be 0 at the leading edge or a number of other conditions, but that wouldn't give you a good agreement with experiment. So the way you intimidate people into accepting this empiricism is you name this condition after some famous people. In this case, it's Kutta and Joukowsky, and there's a debate about which one knew this first or decided this was a good thing to do first. But if you're in Russia, it's Joukowsky. If you're in Germany, it's Kutta. Anyway, that's what we do. And we'll talk more about that when we do the mathematics of subsonic flow. And now let me show you just a few more results since we're talking about results this morning. So far, we've just done two-dimensional flow, but we'll do the three-dimensional case too. And this shows you how CL alpha changes with time for, in this case, a supersonic Mach number 1.4, but for different kinds of wings, right? If we're in three-dimensional flow, we now have to talk about wing, not an airfoil. And so an A will be an aspect ratio, which is basically a measure of the ratio of the span to the chord. So as this number gets larger and goes to infinity, we're back to a two-dimensional case. So if you go back to that earlier curve for Mach number 1.4, where we applied CL alpha versus S, the two-dimensional case is this dashed line. And these other cases are for smaller aspect ratios. Note that as the aspect ratio gets smaller, there's a smaller variation in the lift curve slope, excuse me, with time, and that's typical of three-dimensional flows. Three-dimensional flows are harder to compute mathematically because you're in 3 dimensions rather than 2, but the actual solutions, in some sense, tend to be better behaved. All those wonderful singularities in 2D flow tend to be less prominent and less of an issue in 3D flow. So if you're willing to pay the price of increased computations, there is some gain in that respect. And then finally, I won't go into this in detail, but there are references in the book to this. People have done other more complex. Oh, what happened there? I think I hit something I shouldn't have hit.
The X in the top right, but not the top right. Keep
Oh, I
going
see.
right.
Yeah, thank
Yep,
you.
right there.
How about this? Thank you. I got excited there, or someone did. This is a so-called T-tail. This is a vertical tail with a horizontal tail on top. And T-tails are famous or notorious in aeroelasticity because they're particularly prone to flutter. And the first few times people started building T-tailed airplanes, they ran into some considerable difficulty. And this is a more challenging case to do because now you have to model two wings. You have to model a horizontal wing, you have to model, if you will, a vertical wing, and then the aerodynamic interaction between the two, as well as the structural interaction. But people have done that. You can now obtain a commercial code from Nastran or from the Zona technology, at least in the United States, and probably comparable codes elsewhere in the world that will analyze that geometry and give you results. And here's a typical aerodynamic coefficient here plotted as a result, as a function of the frequency of the oscillation, the reduced frequency of oscillation. Okay. So very complicated geometries are now, I won't say routinely addressed, but they are at least capable of being addressed if you have the right theory and the right code. So I think I'll stop with that in terms of sharing some typical results. You're, of course, welcome to look through the book and study these curves at your leisure, if you have some leisure these days. And of course, I'd be happy to answer any questions. Any questions about these results that I've shown up to this point? Any further questions? Hearing none. Oh, yes, go ahead. Was there a question? No, I hear not. Okay, let me now change subjects. I want to talk a little bit about gust response. And so let's do that. From the aerodynamicist perspective, doing the gust problem is not a big deal. Of course, from the aeroelasticity's perspective, it's the difference between doing a force response problem versus a flutter problem. Depending on whether you're doing the aerodynamics due to motion or the aerodynamics due to external excitation like a gust. But from the aerodynamicist perspective, it's really not that big a deal. The same code that will give you the aerodynamics due to motion will give you the aerodynamics due to a gust. Oops, not quite in the right spot yet. I'll get there eventually. Yeah, I'm getting close. There is some physics here that I want to emphasize, even though the mathematics is very much what we've already done. And we'll do this for the 2D case that we've already discussed. And then we'll, later on, you'll see how that works in 3D and also in subsonic as well as supersonic flow. Here's the idea. If I want to compute the aerodynamic pressures, the lift, the moment, whatever due to a gust, there's a vertical gust velocity, which is really mathematically roughly the counterpart of having an H dot term where I move the airfoil up and down in translation. So H dot and WG to an aerodynamicist look pretty much the same. And they are mathematically virtually the same. But there's one important physical difference that I want to highlight for you. We normally assume that the gust is stationary in a coordinate system fixed with respect to the flow. And the reason you can do that is because most airplanes fly fast enough that the gust changes in time are slow relative to the speed of the airplane through the gust. So, but there is a spatial distribution of the gust field. As the gust isn't uniform in space, it depends on, if you will, x prime, which is the coordinate in the direction of the flow, and in the coordinate system fixed with respect to the airfoil, that is the XT system, that corresponds to what the airfoil sees as a gust, which depends on both X and T, but only in this special combination. So you can think of this as if I'm sitting on the airfoil, to me, that stationary gust looks like it's moving relative to the airfoil with a wave that moves like X minus U infinity times T. So you need to take that into account, that's all. You need to take that into account when you work out the final solution. So now the gust velocity has this dependence. But if you do that, you can go through the analysis. You can still get piston theory, which is what this is. I see a typo. You may want to take this into account because there's some typos I'm going to ask you to look at. This should be a density here and here, not a pressure. And there should only be one in A infinity here, not two. That's a lot of typos in that equation. So, but that is piston theory, and then you can compute the lift due to piston theory, which is a solution for short time, and then you can go ahead and see what happens at large time, and then you can do the full transient theory and work it out just as we worked out the H dot solution for all possible times. So the basic point I want to make to you is that doing the gust problem is pretty much this, aerodynamically speaking, is pretty much the same as doing the motion dependent aerodynamics. Speaking of those typos, which I just showed you, we need another homework problem assignment, right? Because you even though you have one upcoming on Thursday, you have nothing to do beyond Thursday. So beyond Thursday, the next homework assignment, this is number 3 in the series, is to read pages 192 to 235 and find all the typos there. I'm sure you can do that. I just showed you a couple free of charge. So homework number 3 in this series is read pages 192 to 235 and find all the typos that you can.
Well,
Okay.
that's an awful large amount of pages. I wonder, could that be due next Thursday?
Why not?
Alrighty.
A week from Thursday, right?
Oh yeah.
Not next Thursday.
Right.
A week from Thursday.
Exactly.
Yes, you convinced me.
All right. Thank you.
You're welcome. Thank you for asking. Okay, So now, for the rest of the day, I'm going to go out of the screen and I'm going to show you some things that are not in the book but are important. Let's see. No, I don't want to end the meeting. No, I don't want to do that either. Michael, help me out here. I'm trying to get my overhead camera on
Yeah, we're not seeing it either. Do you see? It looks like your video is turned off.
No, it's turned on. But, oh, maybe it's turned off on my computer.
Yeah, on the bottom left, do you see a button that says Start Video?
How about if I go back here? Oops.
We're not seeing anything on your screen right now.
You're seeing nothing.
Nope.
Okay, well, let me.
In the bottom left of the Zoom meeting, do you see a button that says Start Video?
No, I'm trying to. No, I don't see that. Oh yeah, I do. Ah, found it.
Aha.
Does that help?
We see something. Yes.
Do you see it?
There we are. Yes, we see that.
Fantastic. Thank you. Okay. All right. Well, as long as I'm here, let me show another page which relates to the homework on Thursday, and then I'll go on to something else. This just tells you what I said in words a moment ago. You wanted to find a non-dimensional alpha equal to alpha times 2b, okay? You wanted to find a non-dimensional time, which is time times u infinity over 2b. And of course, there's a real time and a dummy time, t and tau. And then you wanted to find a non-dimensional lift coefficient, which is the lift divided by 1/2 rho infinity u infinity squared times 2b. And then you want to be able to plot CL versus T star. And you also want to plot this K function, which itself is non-dimensional and depends on the time difference as a function of that time difference. And you're doing that for two Mach numbers, 2 and 1.2, and you're assuming that dH dt over u infinity is equal to 1. Is that fair enough? You're supposed to say yes.
Yes.
Thank you, thank you, thank you. Okay. All right. Now, let's talk about the following. In this homework, you basically assumed that dH dt over u infinity was 1, or a constant, right? What you really are assuming is it's 0 for time less than 0, and it's 1 for time greater than 0, right? So there's a step from 0 to 1 at time t equals 0. This is usually just called a step change. The nice thing about any linear theory, including the one that we're dealing with up to this point in this course, is that once you compute the result due to the step change, I don't need to go back and do the calculation again for any other kind of change. If I want dH dt to be any whole arbitrary function of time, I can immediately write down the solution in a very nice form without going back and trying to solve the wave equation again. I think you'll agree that that's a nice thing. And it's better than that. If you have a CFD code that solves the Euler equations or the Navier-Stokes equations or any intermediate result, and if the motion is small enough, we have to discuss how small is small enough, but small enough that a linearized version of those codes should give you a nice answer, you can use the same procedure. So you don't have to be, if I have the result for a step change, if I have the result for, say, the lift coefficient due to a step change in angle of attack, or a step change in H dot, or a step change in Gust for that matter. And then I want to know what happens if I have some other arbitrary time dependence of alpha or H dot or Gust velocity, and get the lift coefficient for that case. I can do that in the following way, right? So we're going to talk about impulses and step changes. Impulses and steps. So the way we're going to start off with a non-dimensional. We'll do this in 2 dimensions, but it also works in 3 dimensions. That's even better. But let's think in terms of 2 dimensions at the moment. So here I'm going to non-dimensionalize the lift, and I have a lift coefficient as before. And now the general theory of linear dynamical systems tells me that I can relate the output of the system. In this case, our output to an aerodynamics is, for example, the lift or the moment, or even the pressure distribution itself. I can write that as a linear relationship with respect to some motion variable like alpha or H dot over U or Gust velocity. And I can always write it in terms of this convolution integral, where there is some function I. I use the symbol I because I'm going to think of that as related to an impulse. And therefore, if I find the solution for an impulse in alpha or a step change in alpha, that will allow me to determine I. And once I have I, then I can use this equation over and over again to find the lift for any old alpha of tau. Okay? Where again, the non-dimensional times T star and tau star are given by those formulas. So that's the proposition. So let me pause, because if you accept this, then the rest of it is just a little bit of algebra. So any questions about what I've just said? Okay. Okay, I know some of you are running CFD codes, so you might want to try this with your favorite CFD code. It will work. Okay, so now next thing we're going to do is we're going to drop the star notation because it's cumbersome, right? So now we're dealing just with everything's non-dimensionalized. This is a non-dimensionalized lift coefficient. Alpha is a non-dimensionalized angle of attack, and we're generally a downwash divided by U infinity. Tau and T are non-dimensional at times. So now consider a couple of special cases for alpha. The first special case we're going to consider is alpha as a delta function, otherwise known as an impulse. That's what we mean by an impulse. Now, how would I create a delta function? Well, in an experiment, that'd be really hard. So in a moment, we're going to talk about step functions instead. And step functions and impulse functions have a close and important relationship. But let's start with the impulse function, which mathematically, not experimentally, but mathematically, it's a little easier to deal with. So if I let alpha be a delta function, and I put this in this integral, if this is alpha is now delta of tau, right? Then this integral is just going to become I of t, right? And so the lift coefficients due to a delta function, that's why I put the delta up there to remind myself that this is not any old lift coefficient. This is a very special lift coefficient. It's the lift coefficient due to a delta function. Then if I can ever determine the lift coefficient due to a delta function, then I know what I of t is. It's the impulse function. The impulse function, as you see, is the lift coefficient due to an impulse or due to a delta function. So that's nice. But sometimes, either experimentally or even in computations, it's easier to deal not with a delta function, but with a step. What do I mean by a step? Okay, so this is the impulse. Okay. Now we're dealing with the step case. Okay. And a step is something that goes like this. It's 1 when alpha tau for a step is 1 for tau greater than 0 and 0 for tau less than 0. That's what we were doing in the homework, right? And if you're running a CFD code, it's probably going to be easier to put a step input into your code than an impulse. I mean, there are ways to put an impulse or approximate an impulse, but by and large, a step is a nicer thing to deal with computationally and certainly experimentally. Okay, well, if that's the case, if I put a step in, then this wonderful equation I have up here now becomes this. It isn't, I don't have I right away. I have the integral of I. I have the integral from 0 to t of I of t minus tau d tau. And that's related to the lift coefficient due to a step. And I put the S up here to remind myself that this is not any old lift coefficient, but it's a lift coefficient due to a step. But now, of course, I know the answer. So so I'm about to do something that may or may not occur to you until you thought about a little while longer. But I'm going to help you out. An interesting and valuable thing to do is now to differentiate this equation with respect to time. Okay? If I differentiate this equation with respect to time, I get this result. The derivative of the lift coefficient due to the step with respect to time is equal to this impulse function, which I hope to find at time t equals 0, minus the integral from 0 to t of the derivative of I with respect to tau, not t, but tau, d tau. And so how did I get from here to here? Well, first of all, I need to use Leibniz rule. Leibniz, the famous Leibniz, said, if I wanted to differentiate something that looks like this, there are two contributions. There's a contribution due to the fact that t appears in the limit, appears in the at the tail end of these two of the interval with respect to tau, and also t also appears in I itself. So when I differentiate this with respect to time, is the derivative of the limit, in this case, well, in this case, t with respect to time, which is 1, times I evaluated when tau is equal to t. When tau is equal to t, of course, that's I of 0. That's how I get this. And then I differentiate this thing, the integrand with respect to time. Well, if I differentiate the integrand with respect to t, I would have a plus, and I would have a t here. But since this only depends on the difference and not on t and tau separately, I can also think the derivative with respect to t of I is minus the derivative of this I with respect to tau because of this minus sign that's in front of tau. And why do I want tau here? Because I have the derivative with respect to tau, then I can do this integral very straightforwardly. It's just I of t minus tau evaluated to the limit 0 and t. And when you get that, then this first upper limit gives me I of 0, which cancels this one. And what I'm left with, through the lower limit, which also has a minus sign associated, is I of t. So what I've shown is that the derivative of the lift coefficient with respect to, due to a step with respect to time is equal to this wonderful impulse function. So this is a better way to compute the impulse function using the step change. Okay? Do you follow all that? I hope so.
Yes.
Okay. So what that means is if you have a linear theory or you have small motions, even if you're running a CFD code, don't keep computing. Don't keep running the CFD code every time you change the motion of the airfoil. Find the answer due to a step, and then use this formula for that moment. Because this is fractions of a second to compute once you understand the theory versus running the CFD code, which makes for a much longer day. And finally, then let me note one thing for you. This step function, which is 0 for tau less than 0 and 1 for tau greater than 0, the step function itself, guess what? if I differentiate the step function, I get a delta function. And it's really interesting because you might think I get 0 if I differentiate alpha with respect to tau. Well, you do for tau less than 0, and you do for tau greater than 0, but right at 0, when this thing jumps, it goes to infinity, which is what a delta function does. But yet the integral of a delta function should be a step function, which it is, right? So the derivative of the step function is the delta function, the integral of the delta function is a step function. And that can be very useful, whether you're running CFD codes or using potential flow theory or doing anything else. Okay. That, I think, is all I want to say about that. Let me ask again, are there any questions? I'm going to give you one more thing to do by way of reading material, but any more questions about any of that before I go on? Okay. Michael, do you get all of that, or do you want me to scan something and send it to you and have it in the notes? What would be best?
Yeah, we can scan this after the lecture's concluded.
Okay, great. Do I need to do that, or you going to do that, or?
You're going to need to do that, and the instructions are right there
Okay.
on the bottom of that page.
Yeah. Okay, I'll do that. I'll scan that and send it to you, and then you can distribute it. In fact, I'm going to scan something else also and send it to you. The next thing I want to share with you is the following. This is a little hard to read, I think, but I'm going to scan it and send it to you. Can I make that larger somehow?
Yeah, if you zoom in with the knob on the side of the camera.
On the side of the camera, okay.
Yeah.
Ah. Yeah, you can almost read the title at least, right? And you're going to have the rest of this. This is something that Professor Bliss and I put together a couple of years ago. And one of the things you can do in 2D supersonic flow is you can start out with the general theory, and then you can do one of two things. You can expand it in terms of 1 over the Mach number. And I'll tell you in a moment why you want to do that. Or you can expand it in terms of 1 over the frequency, a non-dimensional frequency. And I'll tell you why you want to do that. And if you do that and write it as an infinite series, or at least a series of several terms, the first term of the series is piston theory, okay? But by including the second, third, and as many terms as your patience will allow in the series, you can reconstruct a very close approximation to the full theory. And the nice thing about that is the form of the theory takes then is much simpler. You don't have Bessel functions floating around and all those other good things. And even including the next term in the series beyond piston theory allows you to get a decent answer down to Mach numbers like 1.2, for example, okay? And then the other nice thing about that is you can not only find the solution on the wing or the airfoil, you can find the solution in the far field, which is important if you're interested in the noise that's being generated from an oscillating wing. So I'll send that to you by way of a scanning. And other than the fact that Professor Bliss and I thought this was neat, and you may or may not agree with that, but we thought it was neat. I guess the more important point is that even now there's still some things to be discovered and improved upon in terms of the potential flow theory. So there's still research going on there, as well as in the Euler equations and the Navier-Stokes equations. I think I'll stop there for the day, if you don't mind, but let me, since we have a few moments, or several moments actually, let me ask if there are any further questions about homework, how you're doing out there in cyberspace. Do you miss being on campus? Whatever else you might like to talk about. What's on your mind?
I miss the basketball games.
Well, let me ask you this question. Based on, I realize you haven't done much of this so far, although I think you have several courses that you're dealing with. How is this distance learning working for you? Is it good, bad, indifferent? What is it?
Personally, I'm not a big fan. I really prefer like being there in person. I think there are some classes where I'm still getting assignments and I'm still doing them, but it just doesn't. It's just really difficult to compare it to being in person, and just it's a lot more like tangible and interactive if I'm there in person. So
yeah. Well, some of you I know, of course, took at least a portion of this course as well as the other courses when you were in Stockholm last year, right? So
yeah, it was kind of the same. Like whenever I took Aeroelasticity from Stockholm, I thought it was a little bit more difficult to follow. I wasn't as like engaged, but whenever I went to Duke, I was like, oh my God, this is so much better.
yeah.
So it's kind of getting used to the Stockholm thing again. I just think there's something associated with like being in person and being able to like see you and see the notes and ask like direct questions. And even though I can ask direct questions, it's just not. I'm just not as like I guess I don't have the same like initiative.
Well, it's interesting because I was thinking as we're going through this experience, I'm wondering whether at the end of the day we'll revert back to how we do things normally, whatever that means, not only at the universities but throughout society. And universities have been talking about going online forever, right? And we've always done a certain amount of that. But I'm wondering if this will accelerate that trend. But from what you've just said, using a sample of one, I'm thinking that people are not going to leap up and say, this is the new way to do it. And now I don't need to come to campus and I can save on rent. And then I can tear down a lot of buildings on campus because the faculty obviously don't need offices anymore.
Yeah, maybe I got spoiled from learning in person. Maybe if you start out online, maybe you can adopt it pretty well. But personally,
well, of course, the question is if the university save all this money, right, by being online, who gets the benefit of that?
Yeah, students, maybe not.
Yeah, that would be an important question. Okay, any other comments or questions for the day?
I would like to add that with respect to the classes from Stockholm, I think Zoom is a better tool to do it. Last time it was really difficult to follow with the technical setup in KTH, but Zoom is much, much better. I think you should probably ask them to use Zoom for the next batch of students.
I appreciate that comment. I think Michael feels that way too. And unfortunately, you won't get the benefit of it next year, but I think we will definitely use Zoom. It seems to be the way to go. But thank you for that comment. I appreciate that very much. Yeah. Any other thoughts? Hearing none. Enjoy the rest of the day. Oh, yes.
I don't know if it only happens to me, but I feel like after spring break when we have the virtual class, the Zoom, I think I'm a little bit hard to follow compared to the previous half semester when we have the in-person class. Especially when you like go through the equations and formulas by your digital book. It's a little bit hard for me to follow compared to like the previous one, just writing down on the papers, and we can like derive the equations one by one. Yeah.
No, I hear that. And if I may comment from my perspective, I enjoy the live interaction face to face. Maybe that's because I've been doing it that way for so long. Perhaps over time we would become more comfortable with doing it online, and of course the technology presumably will continue to improve for online learning. But at the moment, I still think I prefer the live face-to-face venue also. But thank you for that comment.
Thank you, Professor.
Okay.
Well,
Any
Professor
other?
Powell, adding on top of that, I think what Dr. Kilby is doing with his lectures, so like recording the lectures and then have only one day on class discussion, is probably the best way to teach both in Sweden and remotely, possibly, because then you have the time to go over the lecture whenever you want and pause and go back as much time as you want. And then with the in-class discussion, you can answer any doubts and so on. I think I got the most out of my online education from Dr. Kilb's course. And that would be like an ideal model for doing the classes online.
Okay, well, thank you for that comment. I'll talk with Bob about Dr. Kilb about that. So you're saying that he basically records his lecture ahead of time, you watch it whenever, and then you're meeting online and live once a week for a discussion session. Is that what I heard?
Yeah, exactly.
Okay, well, thank you. Thank you.
You're welcome.
Any other comments? Hearing none, then enjoy the rest of your day, and I'll see you online on Thursday.